product is called EMS, electromagnetic or electromechanical simulation. This product has been in the market about 10 years, has always been for the last 10 years as an add-on to SolidWorks. But recently we also branched out to Inventor, and now we have a product integrated in Autodesk Inventor as well. Now the philosophy of our company is really, instead of reinventing the wheel and try to develop some kind of drawing CAD tool, which can never be as good as commercial CAD packages. So using integrating or inside a commercial CAD package is no longer a luxury. It's really a necessity. It's a must right now. So as you can see, this is your regular Inventor. You create your model in Inventor. What you see here, three-phase transformer. This is the core, and there are 3 primary and 3 secondary winding or coils. After you create your model in Inventor, just switch to the EMS Feature Manager. Okay. You can use the Feature Manager tree, or you can use the toolbar. You start your analysis in EMS. Okay, as you can see here, it's fully integrated in Inventor, so there is no importing or exporting or healing the geometry or fixing geometry. It's all taken care of by Inventor, the very powerful CAD package, as you all know. So I start with a new study. So what is a study? A study is a design scenario or a case or what-if scenario, okay, or a simulation. So I'll say add new study, specify the study name, my study, okay, 1, and we have 5 types of analysis. I'll go over them very quickly, okay. So the magnetostatic analysis, okay, is for DC magnetic. You have permanent magnets and or coils where the current or voltage is DC. That's it, don't vary as a function of time. Then you can study saturation effect. You can find your magnetic flux density. You can find force and torques, and a lot of application actually use the DC. Now the limitation of magnetostatic is there is no eddy current. There is no proximity effect. There is no frequency at all. So if you have a frequency problem, and all transformer do, you actually want to use the AC magnetic. Now the AC magnetic, also it's a magnetic analysis, except now you have a frequency dependence. Once you have frequency dependence, there is time variation, current changes a function of time, then there is eddy current generated and skin effect and all of that stuff. Now you specify the frequency, okay? And of course, for transformer, you only compute circuit parameters. Now, why it's an option? Because in some situation, you may be just interested in looking at the field lines, okay? Because the primary unknowns that we solve for using the Maxwell's equation is really the magnetic field H, and from there we derive all other quantities. So all circuit parameters are actually computed as a post-processing from the main quantity, which is a magnetic field. Now, this computed circuit parameters. So what do we mean by circuit parameters? Well, it's inductance, capacitance, impedance, flux linkage, resistance, current, voltage. All of this quantities are called circuit parameters. Now, why it's an option? Because it takes more time. So if you don't need them, you don't compute them. So it's a compute circuit parameter. Now split core loss. Some situation you may want to just find the total core loss in a steel. Some other situations you want to split it to eddy losses, hysteresis, and excess loss. 3 different losses. So if I've seen both customers wanting one, either one or the other. So you make it an option. So if you want to split it, you click on split. Okay. Now, what else we have here? We have also the thermal integrated solver. So in transformer, the heat is really the nightmare, right? So we all know that that one of the primary problem for transformer, they just heat up, and sometimes they reach a point where actually you fry it completely. So for that reason, we added thermal solver. Now, thermal solver is actually a full-fledged thermal solver, finite element. Okay. The advantage of this is fully integrated, as you can see in the study, where you don't need to exit and export and import. Some other company, they have thermal solver, but it's a separate program where you have to export the data and read it in and open and close it. We don't have that. It's absolutely integrated. So the whole idea now is the tight integration, the inventor, and tight integration with thermal program. Now, that's all you need, I think, for your transformer design: the circuit parameter, the core losses, as well as the heat. Okay, let's see AC magnetic. Now, well, AC magnetic, a large number of real-life practical application, they fall under AC magnetic. AC magnetic is AC current or voltage, where the time or voltage is sinusoidal, it's time harmonic. It's a sine curve, You may have a situation where your source is actually not sinusoidal. It can be any arbitrary function as a function of current or voltage as a function of time. It can be a pulse, it can be exponential, it can be anything. So in that case, if you have that situation, you have the transient magnetic. The transient magnetic is a finite element time domain solver, whereas the AC magnetic is frequency domain solver. We have also electrostatic and electroconduction. And this can also happen in some situation, even in transformer design, where you have a very high voltage in the air surrounding or in the insulator surrounding your transformer, and that very high voltage actually reaches a point where it produces corona, sparking, or the technical term for that is the electric breakdown. Yeah, the electric breakdown means the air gets ionized and it starts sparking. So in that case, you want to use electrostatic program module because the electrostatic module will allow you to find the electric field and determine the voltage breakdown or the electric breakdown. Electroconduction is also an electric field solver, except now instead of dealing with insulators, you are dealing with just a system of conductors where there is a voltage difference and you want to find the current flowing in the conductor system. Okay, so say okay. All right, now I have a feature manager has changed. The feature manager is changed by the addition of my study that I just created. Okay. So these are representing various parts. Okay, so you get the core, you have the 6 coils, inner, outer, inner, outer. So 3 primary and 3 secondary coils. You start by applying material. You right click, say apply material. All right. Then you have this EMS library. It comes with the default library. It has a lot of material, but we don't claim that we have all of the materials because there are thousands of, even hundreds of thousands of materials. So if you don't find your material in our library, you can add your own. Lots of resources right now. There is a MatWeb. On the web, you can get a lot of material property, or you can actually, contact the manufacturer of the material from where you bought. They will be glad to give you the property of the material, and then you can build your own library by saying new library, and it's very straightforward to add a material library. Now let's see. I'm going to apply a material right now. It's steel for the core with a steel loss, with core loss. This is right. So the core loss comes with the power flux curve, where you have on the y-axis you have the power dissipated, and the y-axis you have the magnetic flux density in Tesla. Okay, that's your core loss curve. Say okay. Now the nice thing about our material library, you can say, oh, apply. Okay, now apply it to that part. If I want to apply material to the next part, I don't need to right click on the material and say apply again, because my material library is still open in front of me, as you can see. So if I want to, so the next one is a coil, and I could simply say, okay, now I want to apply for this part. I want to apply, of course, copper, and that's the copper. Then say apply, okay, and okay. In case it's same material, you can actually drag and drop. Okay, so these are all copper, so simply I can drag and drop, drag and drop. Okay, now let me just apply now. Say I want to apply air to this part, so I can air. All right. So now when I am done, I say apply and close. Okay, and this really saves you time. Instead of reopening every time the material library, you have it open in front of you, and at the end, when you apply all the material, say apply and close. All right, that's what you need to apply material. It's straightforward to apply material in EMS. Okay. Now, what else you need to do? For the magnetic analysis, really there are not that many boundary conditions. Those of you who are mechanical engineer and do structural simulation, there are a lot more boundary conditions. You have fixtures, you have connectors, you have contact, forces, pressure. In electromagnetic, really we don't have. The only possible boundary condition is normal flux. If you have symmetry and the flux is normal, specify that. So most of the time we don't apply any boundary condition. Now, for the heat part, we're going to need to apply. Now, as you can see, the load or restraint or boundary conditions are integrated. You can do the magnetic as well as thermal, right, in the same dialog. So if you have, it's a full-fledged thermal solver. If you have temperature, okay, if you know the temperature in the model, or additional heat flux. Now, you don't need to put any heat flux or volume heat. That is, which is caused by Joule losses or eddy losses or core losses, okay? Because EMS automatically takes all the losses and apply them for you as a load, a thermal load in the thermal solver. So except just if you have additional, I don't know, maybe next to your transformer you have a fan heater, and you could have additional heat, not due to the losses. Okay, you could apply one. So most of the cases is just convection. So the transformer are usually in they're either most of the time they are in oil or air. Okay, so you choose the parts, okay, which is the air part. This is the convection coefficient and the ambient temperature, and you apply your convection, right? Okay. Now, next thing is how to apply the coil. I know a lot of programs. It's very complicated to apply a coil. So let's see how it's done in EMS. And of course, the coil is the heart of the transformer. So, okay, let me first of all hide the core. You can do visibility without going back to the Inventor Feature Manager tree. All right, now I hit the core. I want to apply. I want to apply now a coil. So let's say I'm going to apply my inner coil. Okay. Right. Again, I'm used to the right click, but you might as well use the toolbox. So I say on coil. All right. Now, a coil could be current driven or voltage driven. So what does it mean, current driven? What current driven means, the current that is flowing into the coil or the winding. Okay. In some situation, you don't actually know the current flowing in your coil. You only know the voltage and some RLC circuit between the current source and your winding. So in that case, you can specify voltage driven. All right, let's go to current driven. Most of the cases are current driven. Now, this is what we call AWG, wire gauge. Specifying this will the right wire gauge is going to help you in finding the proper DC resistance, because based on the wire gauge, we compute the DC resistance. You don't need to enter it. We automatically compute it for you. In case you have a fraction, this is a full problem, because for symmetry purposes, sometimes you want to do only half of the problem. So you could put half or quarter. So in this case, it's entire problem here. So let's see now. Now I want to choose the parts that make up coil. Okay. And also I want to choose how the current is going to flow, because the current can flow clockwise or counterclockwise. So let me see if I can do select other. Okay. Wait. If I can select that particular face. No, I'm not able to select it. Okay, so phase 2. Okay, so that's the face. So it's gonna the current is gonna flow counterclockwise. So once you select the inner face, now one important thing is you have to always split your coil to 2 if you have a multiply connected or a loop, because you're going to need to have access to an inner face to apply the sense of the current. All right. What else you can do? Number of turns. You can specify the number of turns. RMS current per turn. okay, and the phase. Okay, so and say okay, that's how to apply the coil. Then you can apply the for all other winding or coil the same way. Now we may ask, okay, why it's represented by those of you who may be mechanical engineer, why it's just represented by one block, one volume coil. It's actually, the coil is not a continuous block. It has wires wound around the movement most of the time. And the answer is you don't need to do that, because if you put individual wires, okay, they're going to complicate the geometry and the meshing without benefiting anything from that. Why? Because by representing it, okay, by saying this is the volume and specifying the number of turns, the simulator knows it's internally it's going to take care of that for you. Okay, so there is no need to model individual wires. And if you want, yes, the EMS can handle that, except now it will take a longer time to mesh and solve. All right. Then meshing. All right. In some situation, you want to be able to apply mesh control. Why a mesh control? Okay, because in EM, we have to deal with the exterior domain. Well, be it oil or air, they have to truncate. We have to consider it, include it in the simulation. Okay. Why? Because electromagnetic field or wave can actually propagate even in vacuum, let alone in insulator or conductors around. So you have to include it. And if we were to a fine mesh for the entire problem, you're going to end up with a huge mesh, million of unknowns, which is going to take a long time to solve. So to make it simpler, we've added this apply mesh control. So what is apply mesh control? I could apply, for instance, if I want to mesh control on this part, okay, and maybe on this face, okay, and now I can specify maybe the element size, okay, for instance, I will say 0.01, okay. Okay, I can show preview symbols. Okay. I say okay. For wherever I apply the mesh control, okay, it's going to try to respect that control as much as possible, as close as possible when it meshes. Okay. So when I do create mesh now, what's going to do for me is going to mesh all the part using this average number of mesh element per diag, or you can specify the mesh size. Okay. And then except where you have mesh control. So if you have mesh control, it's going to apply that mesh control, not the global mesh size. All right. And meshing is also very fast in EMS. So let's go straight now to the existing study that we solved it to show you what you end up, what kind of results you have at the end. Okay. So this is my mesh. If I can toggle mesh. Okay, so I can toggle on and off the mesh. So it's not very, very dense mesh, but it's adequate for this type of solution. All right. And I applied 6 winding. If you look at the winding number 1, you're going to see that the phase is 0, and winding number 2, the phase is actually 120 degrees or 2.09 radians. All right. Now, if you look at secondary coil actually has number of turns, but there is 0 applied current. Now, the, you may ask if there is no current, if there is no applied current, why do you have to represent it? Well, the answer is because there will be current and voltage induced in secondary cores. And they're going to also be used to find the inductance matrix. All right, so we have 6-core system, and they're meshed. By the way, you can, the order is very important. I mean, you could start by meshing, or applying core material or load restraint. It doesn't matter as long as you do all of them. And if you forget one of them, the simulator is not going to run. It's going to remind you that you're going to apply. You didn't mesh it, or you didn't apply. You don't have any coils, or so on and so forth. All right. So if you look, once it solves successfully, you have results. So you have many folders representing different results. So first results, we call it results table, or tabulated data, or lumped parameters. Now these are quantities you can't represent on the mesh. It's not a distributed quantity. It's just like energies, the whole energy in the system. Okay. Now then you can look at these are your electrical parameters. You can look now at the inductance. This is inductance matrix. 6 by 6. All the time you have the surf terms and the mutual terms. As you can expect, always the mutual terms are negative. Inductance matrix. Impedance. Please let me just. Then you can have the impedance matrix. Coupling coefficients between various winding, losses. Remember that I had a loss just in the core, right? So the other stuff is in the core. You have the ohmic loss, eddy losses, hysteresis losses happen to be 0, excess loss, and this is total the core loss. All right. Now this is a current that I apply, and you can, and the voltage. So the voltage in each winding is also calculated. Okay. Flux linkage. These are the tabulated data or circuit parameters. So you can export this data to an Excel sheet, export all the results to or a text file. You can print it, okay, or close it. All right. Now, once you look at the electrical parameters, and again, the electrical parameters are really related to the field. Okay. So they are actually post-processing. We don't solve directly for inductance. We don't solve directly for current we could, or for flux linkage, or any of these quantities or energy. We solve for the field, which happen to be the magnetic field in this case. From there, we derive all other quantities. So if you look at your results table, and it's not what the results are not as you expected them, you may want to know why. And to find out why, you have no option but to examine the field. So you have to have the proper field circulation. The fluxes have to circulate in the right direction, minimize the leakage, and so on and so forth. So these are the field solution. Now, as you can see, there are about 8 or 9 folders. All of them are quantities that you can plot on the mesh. So start with magnetic fluxes, which is the most important, B. Okay, it's called B usually. And the magnetic field is then applied current density. You want to see whether the current that you applied is actually the right circulating in the direction, the desired direction, or not. Okay. Then you have the current density, and that's eddy current in conductors, induced current or eddy currents. You could also compute the force density per node. It's like a pressure, you know. Electric field, losses, loss density, temperature gradient, and heat flux. So both solvers or their results are also integrated in the same environment. All right, let's start by looking at looking at the applied current density. Okay, so if I do 3D plot, I can plot any component of J, okay, or the resultant. I can choose different units. I can choose fringe or vector. Let's just choose vector now, okay, and say, okay, validate. All right, so now I have a separate windows where actually I can examine my results. So as you can see, the current is flowing in the proper direction. Okay. So I'm okay, because if you make a mistake and instead of choosing an interface, you choose a face from the bottom or top, you're going to see that the current is flowing up instead of flowing around. So it's good to examine your applied current so you feel confident about your results. Now, next thing you can plot is the magnetic flux density. All right. Fringe, again, in the fringe I have continuous, discrete line or points. You can have real or imaginary, because don't forget this is time harmonic. So the quantities, the magnetic flux density and magnetic field, are complex quantities. So you have real and imaginary, you have magnitude and phase. So let me just plot the magnitude in this case. Okay, so this is the magnetic flux density. So it gives you an idea about the maximum magnetic flux density, say, in the core. Okay, and if you want to do further analysis on that, there are several tools. One of them is chart options. I can see the min and max. Okay, I could also show min max on shown parts only, or I could also change the range. If I want to see it only within a certain range, I could definitely do that. As you can see, it's changing. Okay, so if I want to see the field between 0.09 and 0.01, I could do that. If I want to go back to 0, right? These are also some goodies here about where you want to place your legend, position, color, format, so on and so forth. These are all nice options to use them once you look at your plot. Okay. Now, next thing I can do is I can actually dissect it. Okay. So, yeah, fine, from outside looks fine, but what is going on inside the transformer? For that case, I do section clipping. Now, the section clipping actually it allows me to look at one particular section, okay, that I can move, okay, different position, okay. You can add a second section, different plane, and the third section, and the fourth and the fifth, up to 6 section all superimposed. And I understand beyond 3 it becomes really cumbersome, but sometimes you want to do like 6 sections along one same direction, and you want to see how the field varies from one section to another. So that's the section plot. Okay, and the section plot is available for all field quantities. For all the vector plot, also you can also do a section clipping, as you can see here. Look at the vector plot of magnetic flux density. Come on. All right, it's coming now. So it's no brainer, you know, the magnetic, this is, you can see how the field circulates in the core. Okay, now I can also section that vector plot. Okay, and sometimes it's very relevant to see your vectors inside. Okay, I can say inside out, and if the vector are not visible enough, the vector plot comes with vector plot options. Where is my vector plot options? Okay, I want a vector plot. Okay. Okay, a vector plot options allows me to, if I want to make the size longer, becomes more visible, as you can see. It depends on situations. These are longer vectors. The density, if it's too cumbersome, I can make it less dense. Okay, different shapes. I can have filled shapes. I can use arrows. There are so many different options in the vector plot as well. So that's the vector plot. Now, why we care about vector plot? Because the vector plot are the plots that gives us the direction of field lines, how they're circulating. Okay. And you want your field line, your transformer to remain within the core. You don't want any leakage, because if you leak, there is loss. So it's very important to be able to do the vector plot. Another type of plot, probably can do it this time on the eddy current, is 3D plot. I can do again resulted, but now it's strange, but I can do now lines instead of continuous, okay? And you can specify the number of lines. Okay, so as you can expect, eddy current is only, well, this is showing even the current in the conductor. So if I want to go back and try to isolate, see if you can isolate. I cannot isolate, so I could probably hide the okay. Let me see if I'm not sure if Inventor has isolate. Yeah, here you go, isolate. Thank you. Okay, so now I'm gonna go to the EMS, and if I click again on my current density, I should be able to see only the core. All right, here we go. It works fine. All right, so this is my current density, or eddy current, my core. So again, I can do a section clipping. Okay, I can plot on section only, or I can choose different planes. Okay, change the number of lines, and as you can see here, the penetration is only on the skin. That's why it's called skin effect, and your current eddy current is going to always remain within the one skin depth. Okay, so if you see some eddy current right in the center, then you know that there's something wrong with your design. All right. Another type of plot, of course, now once you're satisfied with electrical parameter or not satisfied or you know where to change, you may want to look at, of course, there are losses, you can plot losses, okay? You may want to look at the temperature. All right, so you're going to see, okay, now what is the temperature in the system, okay? Well, in this situation, I see that I have a maximum temperature of 61.4 C, which is not a lot, okay, which is probably this is a good design. But if you have too much losses, temperature will be very high. So this is a very useful tool, looking at the temperature and the temperature gradient for transformer design. Yes, it does. Okay. Oh. Okay. So now I can do the same thing. I can do my section clipping. There's another feature. Actually, maybe I can demonstrate it. And this one is ISO clipping. Sometimes you want to know only a certain range of values. Okay. Suppose I want to see only between 26 and 57 degrees. You can see that. If I want to limit it further, I can do inside out actually. Right? Do inside out. Alright, there you go. So this will really pinpoint to you the spots where you have high temperature. Because you can say, okay, now I can see where I have a temperature between 59 and 61. Okay? And you go to that spot and try to design around it or fix it. So this tool, the ISO clipping, also can come in very handy. Okay. Another type of plot. Now these are color plots. Sometimes you say, okay, now fine, color plots are nice, but I want to see some numbers. You know, if I want to see how the temperature, for instance, varies between say between this point and say this point over here, I can choose different tools for temperature. Say, okay, I want to see how the temperature changes along that segment. Let's say, okay. Now, it's taking that segment, subdividing it to about 20 points, and giving me the temperature along that segment. You can have many segments, actually. You can 100 segments, doesn't matter, you know. So, as you can see now, 0 being 0.1, and this one here is being 0.2, so I can track, see exactly how my temperature varies along that segment. And I know that in the middle is reaching a maximum of 57 degrees. You may want to list it to actually see numbers, because really color plots are fine and nice and all of that, but oftentimes you have to map between the color and the value. The value, if you are in this color all the way between but this tool gives you exactly numerical values. So you could also export, save it or export it. There are a lot of goodies here. You can zoom in, zoom out. You can make it smaller, bigger. It's really it's a very nice 2D plot that gives you a lot of features. You can change the colors. You can have as many plots as you want. So again, eventually you could print preview, and or export it to an Excel file or a text file if you want to do further processing on it. So the 2D plots are available for all data on the mesh. Okay, anywhere, for any of them, you could actually do a 2D plot or on a segment or many segments. I know if I want to do, for instance, I don't know, magnetic field 2D plot, I don't have to choose just one segment. I can choose this. So then over here, this, then I go here, then I go here, and then, you know, so there is no limit on the number of points. Between each two points is going to subdivide it to 20 or 30, or you could have even 1,000 points in between. Okay. Now it's giving me some, it's taking more time because I have more points and it has to search for all of these points. So as you can see here now, it's a different curve. So, all right. After you do the work, you want to document it. And documenting it is a main part of our job as engineer, to document our work. You could do the best work. If you don't communicate it, don't document it, share it with other people, it has no value. So we also automated the documentation, so by generating a report. Now, the report, all right, the report has different sections. You can pick and choose which section you want to include. If I want to have no description, I can uncheck it. I don't have any file information, I can uncheck it. So you put your company logo, title, company name, a date is always stamped for you, and time. Okay, and then you may want to. Then you have an option, choice between an HTML in case you want to share it on the internet, or a Microsoft Word file. Okay. And once you say OK, it's going to now dump all the data for you. Okay, the input, mesh information, the excitation information, all the results table, all the plots, or in a concise Word file. And as you can see, a Word file here again is integrated in Inventor, and I'm repeating myself. You know, the whole idea of our company is making it our design tools easy. As you can see now, since I started not close Inventor, I'm always in the same page. I can do all of that stuff right in the same environment without closing my or changing windows. All right, now why is it giving me this? Because I clicked on it twice. So now this is my report. Okay, so it's a regular Word file. It's normal Word file. You can edit it. Okay. These are the materials, coil information, study properties, and these are the results: current, voltage, flux linkage, losses, inductance, impedance, coupling coefficient. These are the plots. Okay, and because it is a Word file, you can definitely generate and print it, or maybe you could generate a PDF file. So that's okay. So after you document your results, say, okay, now I want to make a change, say the current, or the voltage, or material, or anything, any design parameters. The question, do I have to go through all the pain of repeating all the steps? And the answer is no, because EMS allows you to drag and drop. If you take this study and drop it, it's going to give me a copy of one. So what does that copy have? It has everything in the previous study. So I can save a lot of time by just copying my study, cloning my study, keep my previous study. I don't want to, because sometimes you say, okay, why don't you just modify the values of this study? Well, you may want to keep those results to compare them. Okay, so I'm keeping my old study or my old scenario. Now I'm creating a new scenario, but I don't start from scratch. I start from a clone study from that I created previously. Now, it can take a minute or two because it's copying all the data for you, all the core information. Now, there you go. Now it's my study. If I want to go ahead, okay, fine. Now I want to change the current. I want to see our number of turns. Okay. See, okay, can go ahead and change it. Okay. Then I can then run my study. Okay. Let's see if we have added this. Run all studies. Oh, here we go. All right. So you could also generate maybe 10, 20, 100 studies before you go home in the evening, and you can run all studies. And when you come in the morning, okay, you're going to see them. I see all of your results. Then you can compare your results, or if you can compare the results, the tabulated results, or circuit parameters, so to speak. Or in 2D plot, you can actually, let me see if you have implemented this or not. Yeah, I don't think we have it yet in this version. So, because in the SolidWorks version, we have you can actually compare between different plots from different studies, be it flux density, current, or temperature, and so on and so forth. So, that's basically what I have to say today. I don't know if you have any questions. Okay, let me go back to the model actually, and do isolate. But I think somebody asked about the air gap. Yes, of course. These are air gaps here, as you can see. These are air. So because it's finite element, there's no limit on the complexity of the geometry, because at the end of the day, us as computational people, we only care about, we see things as a mesh. So as long as we can mesh it, we can solve it. Because internally, we look at one tetrahedron at a time. So you could have air gaps, you could have a very complicated geometry. It's really, your computer memory is the limit. Okay. Okay, let me see. Let me see the question. Okay, I would like to avoid signing the convection coefficient.
Excuse me, Ahmed, prior to that, there's a question prior before that, which is, do you run studies sequentially or in parallel?
Okay. Let me say, ask the first question from Corey.
Okay.
Handle the air gaps in core and stated dedicated classes. Yes, it does handle air gaps in core or in winding. Okay, because as a matter of fact, I could actually close this one here, close this, okay, and open another one where we have air gaps for cooling purposes in the winding, which is probably a more realistic example. Okay, so if I look at my final assembly, all right, now I'm take another actually three-phase transformer. As you can see, I have the winding. Oh, file is just there are air pockets in the winding for the quantity are complex. So you have to store the real and the imaginary part. And when you do simulation, when you start solving, if you do a matrix, as those of you familiar with the matrix solutions, you do a lot of matrix vector multiply. If you do a matrix vector multiply for real, it's much faster than complex vector with complex matrix. So these are vector, these are complex vectors. That's why it takes longer. How many elements for this study? Okay, for the previous one, I think about 400,000. For this one, mesh details, it's 956, 833. It's almost 1 million elements. Okay. Now, why? Because of this, these are cylindrical. So if I toggle mesh, you're going to see. Okay. It takes more mesh if you have a cylindrical geometry. So this is my mesh. Yeah. The Inventor version became available. I think we shipped the first copy last June 2013. How many degrees of freedom you solve in the 10-minute solve? All right. Let me see. Let me see this one here, the log file. In this particular case, I can look at the log file, by the way. Okay. All right. So this particular problem. Do I have the number of degrees of freedom? And actually, all right. Number of edges, 1,176,060. Okay, I think this one takes longer. Okay. In EM, we use something called vector finite element. So what does that mean? It means that the shape functions are not actually placed in nodes, are placed on edges. And that's further complication because you always have much more edges than nodes. So in this case, I have 1 million, more than 1 million edges. So if maybe 1,000 of them, 2,000 of them are known, actually don't have any directly bounded conditions. So these are basically the number of unknowns for this particular problem. Okay, the previous one is less. Okay, and this 1056. How long it started? Okay, this particular one is 1 million elements. Started at 1026. It ended at 1056. So about 30 minutes for 1 million elements. Not bad, right? For a complex vector solver, it's really considered fast. So, okay, you see the next question. So for the 10 minutes, that could be probably, I can open it, but it's probably somewhere around 450,000 or 450,000 degrees of freedom. Okay, we'd like to extract the formulas per component. Okay, so if you look at my results table here, I don't know if this one has the okay, losses. Okay, as you can see, the losses are per component. So air, solid, whatever. So you have the ohmic loss, eddy losses that happen to be 0 in this case, but so to extract the power losses per component or partial components such as a single coil utilized in separate CFD. Yeah, so every single part has its own value for losses. Okay. The previous example we had some core loss, but in this one we only have ohmic loss. Okay. Are their stats? I don't fully understand the question of stats. So what do you mean by stats? Mr. Ozan? Are there stats? I don't know what means stats. Thank you. Okay. Oh, statistics. Yeah. So the log file, okay, has the statistics in terms of the on the run. Basically, you have when it started, when it ended, and the number of elements, number of faces. And don't forget, these are 5 pages, not only one. Okay. So the time it took for each one of them. Okay. Okay. Thank you. Okay. Let me go back here. Okay. All right. So there are no more questions. If anybody has any questions, I'll be glad to answer it. So,
okay.
So to summarize, just one second.
Go ahead.
To summarize, the combination of power of Inventor, the CAD power of Inventor, so to speak, along with the power of EMS, tight integration, and EMS, as you saw, it has all pertinent design quantities, being the flux density, being the flux, being inductance, current, voltage, losses, core losses, temperature, and all of what you need for your transformer design. Okay, it makes very and the ease of use. It makes it rather easy and efficient to do your transformer. You either start a design from scratch, maybe, or maybe you could just verify your experimental data. So it can be very useful for your transformer design. Thank you very much. I don't have any more points. So if there are no more questions, I'll turn the presenter to Adam.
Yes, thank you, Ahmed, for your presentation today. I wrote there. For any sales questions, please send an email to sales@emworks.com. For technical questions, please send them to support@emworks.com. This webinar will be posted on our website, www.emworks.com, starting from Monday, so you always can download it and look at it there. And we do have more webinars coming next week and the week after, so please stay tuned. I mean, they're all posted on our website. Thank you all for your time. It's much appreciated, and you all have a good day now. Bye.